All right. So today's lecture, we're going to focus on actually relating hydraulic conductivity to porosity. And what are some of the key assumptions that are being made? Now, this is a short lecture, but we want to take some notes as to, what this equation is and when it is appropriate to be used. So the Closny-Kármán relationship is actually between permeability, that's little k, and our total porosity. Now, when we apply this Closny-Kármán equation, we are applying it typically in an environment with well-sorted sand and well-rounded grains. Now, that is generally not what you're going to run into out in the field, but it is a start at least. And sometimes it's one of the ways that we just begin to think about the relationship between these different materials. So in this instance, K is the permeability is equal to the porosity cubed. So that's the raised to the third power multiplied by the grain diameter. Now, remember, your grain diameters are going to be pretty small. So you're going to want to be careful of your units here when you start to solve between these so you understand what the unit is that you're using, that you're actually coming up with your permeability values. So that permeability value is going to be solved by n cubed times your diameter divided by 180 multiplied by 1 minus your porosity all squared, right? So you're going to take first the inside, so the opposite of your porosity, essentially. You're going to square that term, and you're going to multiply it by 180. Again, this equation only works in well-sorted sediments. And things are much more complicated in rocks and sorted and kind of mixed sediments themselves. Now, note, we said the idea when we began this lecture was to be able to rate it to hydraulic conductivity, not permeability. So we have to take a second step in this situation, right? We have to take our permeability that we're solving for using the Closny-Kármán equation, and then we have to use the properties that we know of water itself, right? Our density, our gravity, and our viscosity to turn that permeability value into a hydraulic conductivity value. So I want to ask you to take the time at the end of this, right, to solve for these two. What is the hydraulic conductivity of a well-sorted sand with a porosity of 40% and a grain size diameter of 2 millimeters when groundwater temperature is 10 degrees Celsius? Additionally, how much would you have to change if your groundwater was 20 degrees Celsius? So how much would this value change if your temperature just raised a small amount? So that can give you kind of an idea of what happens when things like temperature or thermal gradients change in the groundwater and what that means for the rate at which water can flow through the subsurface.